don't know why, but I feel kind of dark and shadowy today. Maybe it's because we're a little later in the day and it's a bit of rainy kind of looking day out there. It hasn't rained much, but it's not a bright sunny day. But we're supposed to have some of those. So by the time I have this video, hopefully you got some really nice warm weather coming our way. It's supposed to be getting nice with chances of rain all the time. But 70s and 80s. So hopefully we'll get to that. We are just like a couple lessons from finished. Finals are supposed to start next Thursday. That was when finals start, so we won't have any lessons past that. Next Wednesday will be the last day we post anything, and it's gonna be like a fast Friday. And don't worry, that's gonna be an easy day because it's our last official class day. So log on there. I want you to see what we got. So we'll have this lesson. We'll have a lesson Monday, Tuesday. And then Wednesday, wrap it up. And we don't hardly have anything left. Now, I do know instead of finals, there is some kind of community project thing the school will be getting you information on if they haven't already. So instead of finals, it's something where maybe you go hike a trail. I don't know. You have choices. I haven't even seen the choices yet. It's like you go hike a trail, take a picture of yourself or something. But, I mean, it'll be some community things that you can do safely. And just have some fun rather than having to study and answer a bunch of questions, right? Much better. So let's get to it because we don't have a whole lot left, right? We're going to get to our lesson. That's not it. That's this here. This hand. That's not our lesson. That's not our lesson. Just something I saw and enjoy a little funny stuff on that. But hopefully you get that feeling pretty regularly, though, right? No, this is what we were looking for. This is it. Okay. So, we're going to jump to lesson 8. Like I said, we've only got a couple lessons left. We don't have time to cover all the circles. I just want to pick out some of the good stuff that you need to know, some cool things that we can learn about circles here to wrap up the year. All right, math talk. Fractions of a circle. A fraction of a circle. That means a portion of it, right? A fraction is just part of the whole. We're talking about part of the whole. All right, fractions. Find the area of the shaded portion of the circle. Area of a circle. Pi r squared. Unless your pi are round. I don't know how your mom cooks. Pi r squared is the area of a circle, right? That's area formula. So, radius is 8. So, 8 squared, 64. 64 pi. 64 pi would be the area of that circle. We don't have to put that in the calculator. We don't need to know the decimal equivalent of that. 200 point what. No, this is the answer. Leave it like that. Find the length of the highlighted portion of the circle's circumference. All right, there's circumference. Circumference of a circle is either pi times the diameter, or if you don't have the diameter and you just have the radius, 2 times the pi times the radius, right? Because it takes 2 radiuses to equal 1 diameter because it's half the length instead of the whole length. So either one of those is circumference. We have the radius. So the circumference of the circle will be 2 times 8 pi, so 16 pi. But the highlighted is only half of it. So half of 16, 8 pi. 8 pi would be the circumference, the distance around the outside of that circle. Find the area of the shaded portion of the circle. Well, this is 6, all right? 6 is the radius. So the whole circle, we know, would be 6 squared is 36 pi. But we don't have the entire shaded circle. What do we have? That says it's a 90-degree angle. That is 90 out of 360, right? That is 90 out of 360. The whole circle is 360. That's the same as 1/4. We have 1/4 of the circle. So we can divide that by 4 or take it times 1/4. Same thing. Times 1/4 or divided by 4. 9 pi. 9 pi is the shaded area. 9 pi. 36 pi times 1/4. Times 1/4. Same thing. Okay, let's look at this last one. Find the length of the highlighted portion of this circumference. Again, we've got the 6 as the radius. Now we said 2 times the radius times pi would be the circumference. So 12 pi. But again, we've only got 1/4 of it. So 12 pi times 1/4 is 3 pi. All right, 3 pi. because we multiply it straight across. 12 times 1, 1 times 4. 12 over 4 is 3. Same as dividing by 3. 3 pi. Okay, so you kind of get the idea of what we're looking at here. If not, backed it up. It's just a minute or two. But we're going to play with it some more. All right, a sector of a circle. A sector. Another vocabulary term about circles. Like I say, we can do a lot with circles. A sector of a circle is the region enclosed by 2 radii. So a radius and another radius. So looking at this radius here and this radius, there would be 2 different sectors, right? Because if I'm talking about the white area, that's enclosed. But the shaded area is the outside, so it's only the larger. So we're talking about this sector right here. Okay, so we could have this sector right here. We could have this little sector right here. We could have that sector right there. Those are all sectors. That's part of a circle, part of the area, the inside, the whole area. So for each circle, find the area of the shaded sector and the length of the arc. So we got to find the length of the arc that outlines the sector as well as the area of that sector. All units are in centimeters. Give your answers in terms of pi. In terms of pi. That means don't put it in your calculator and multiply and get the decimal. Means if the answer is 8 pi, that would be in terms of pi. There's 8 of them. There's 8 pi. So in terms of pi means don't use your calculator. Okay, so we have 10 as a radius. The area of our circle again, area pi r squared. We have the radius on all these, so the circumference, if we need it, 2 times the radius times pi, or 2 times pi times radius, whichever order you want to put that in. We're multiplying all 3, so you can multiply it in any order. So, 10 times 10, 10 squared, 100. 100 pi. That entire circle would be 100 pi, right? 100 pi would be the area of the entire circle. We do not have the entire circle. We have 270 degrees. So 100 pi times 270 divided by 360. That's a ratio. Of the 360 degrees, we have 270 of them. See, we don't have all 360. We have 270 of the 360. I'm going to get that a little closer. Just a smidge. All right. I get that twisted on. What did we... Oh, okay. 270 over 360. What does that simplify down to? Well, that's 90, 90, 90. That's 3 90-degree angles. So that's 3/4. Because there's 4 90-degree angles altogether, right? If we had this straight across there, that's 4 equal sections. So this is the same as 3/4. So what's 3/4 of 100? 100 pi times 3/4 is 75 pi. It's easy when you talk about 100. You can think about $1. What's 3/4 of $1? 3/4. 3/4. 75 cents. 75 pi. That's the shaded area. How about the length of the arc? Okay. 2 times the radius times pi. So that would be 20 pi would be the entire circumference. So the length of just the arc would be 3/4 of 20. So that would be 15 pi. 15 pi is the length of that arc. Let's look at this one, 60 degrees. Oh, now we're getting away from the 90s. It was easy to think of 1/4 and a half and 3/4, but now we have 60. Let's find out the whole thing first. 12 squared is 144, so the whole circle would have been 144 pi if we had the whole circle's area. We don't want the whole circle. 60. So instead we have 60 out of 360. What does that simplify down to? Well, 60 actually goes into 360. 60, 120, 180, 240, 300, 360. This is the same as 1 over 6. Right? 1 over 6. Because we can divide the top and bottom by 10. That gives us 6/36. 6/36. So that still we can divide by 6 over 6. 1 over 6. 1/6. So 144 times 1/6. Let's see. 144 pi times 1/6. Let's see. We can use our calculator just to make that simple. 144. Let's do times 1/6. I'm not going to put the pi in there because we're going to leave it in terms of pi. 144 times a sixth is 24. 24 times 6 is 144. So 24 pi. That is the area of that shaded sector. 24 pi. How about the arc? 12 times 2 is 24, so 24 pi would be the circumference. I've got 1/6 of the 24. 24 pi times 1/6, or divided by 6, since I just have one of them. 4 pi. So 4 pi is the length of this arc right there. 4 pi. Okay, not too bad. Let's look at this. Now we got, okay, well, 135 over 360. Let's do the whole thing first. 16 squared. Area be pi 16 squared. 16 times 16 is 256. So the entire area would be 256 pi. That's the area of the entire circle. We only want 135 degrees of it. We just want a sector that's less than half but more than a fourth. So 256 times 135 divided by 360. If you can't simplify that, and it simplifies, but it's not a nice easy one necessarily, like a half or 3/4, you can always use it exactly like it is in your calculator. As long as you set it up properly, 256 times, and then I'm just going to put in parentheses 135 divided by 360. Use it exactly like it is. 96 is the answer. 96. So, 96 pi is how large the sector is, the shaded area. So, 135 3/60ths is like 3/8. 3/8 is what I think that probably boils down to. Let's see. 135 divided by 360, and it's 0.375. And our calculators can give us that answer. Oops. Wait. Back that up. Fraction. There it is. 3/8. 3/8. 3/8. 3/8. It's 3/8. We need to figure out how long the arc is. 16 times 2. The entire circumference would be 32 pi. 32 pi times 3/8. 32 times 3/8. 12. So 12 pi is how long that arc is. 12 pi. 12 pi. So it's just a matter of just setting up the fraction. You can always simplify it, but you don't have to. You can put it into a calculator exactly like it is. Just don't put pi in the calculator. Put pi at the end. See, I didn't even write it down on this one because I just wanted to know what the 96 was. And then I put pi on it because I know it's times pi. They're all times pi because it's area of a circle. It's the circumference of a circle. So, onward. Are you ready for more? We are. We're going to try this. There's a Greek mathematician named Eratosthenes. Them Greeks. Eratosthenes. And he calculated the circumference of the Earth more than 2,000 years ago. Over 2,200 years ago. And he used information similar to what's given here. So, I have a video. I want you to watch this video that I have I found, and I'm telling you about it here for one of our different Greek mathematician buddies. Watch this video. Eratosthenes. How would you set about to measure the earth with the mathematical knowledge and the tools that you already possess today? A Greek named Eratosthenes, he did it 240 years BC, over 2,200 years ago. He was the head of the Great Library of Alexandria in Egypt, a city built by the Greeks. He, like others, suspected that the world was round. After all, the sun and the moon were round. He also noticed that the sun's rays fell in parallel lines. Greeks before him had divided the circle into degrees and had measured the angles. So with this information and a logical mind, he measured the earth. Here's how he did it. While visiting the city of Syene one midsummer's day, Eratosthenes noticed that the reflection of the sun could be seen in the bottom of a deep well. The sun was overhead and the rays pointed straight down to the center of the earth. He remembered this, and on the next Midsummer's Day, when he was in Alexandria, he measured the shadow cast by an obelisk. Sunbeams travel in parallel lines, so the difference in angle had to result from a curvature in the Earth. If the angle was 1/50th of a circle, then the distance around the world must be 50 times the distance from Alexandria to Syene. With these simple tools, Eratosthenes made this almost exact measurement of the world more than 1,700 years before Magellan sailed around it. He was a friend of Archimedes. He was a mathematician and a poet. He invented the sieve for finding prime numbers. He was the first geographer and corrected the calendar to the one we use today. So, Eratosthenes had basically no more knowledge than you currently have right now in geometry. You could basically do the same type of stuff. Look at that. It was bright for a moment. The same stuff that he solved right there with the tools that you have. He just put a little logical thinking to it. He said, well, if the rays come straight down, and here I saw them go straight down the well, so I know they were coming exactly straight down. So he waited till the next year on the same date, June 21st, where he knew this was the case here, and he was 2,500 stellines away, or whatever their measurement was, about 50 kilometers, in Alexandria, and he was there. He said, well, the rays should come straight down. If they come straight down, they should both come straight down. And what he saw there is, oh, there's a shadow. So that this has a shadow. It's cast a shadow. So the only way that this could be straight and this not is there must be a curvature. There must be, they're not flat. If there's a flat, they'd be straight down in both places. It's got to be a curvature. So he said, well, I take this distance, figure out that angle, then I would know how much of a circle they are apart, because I could just figure out what that angle is. Cool stuff. So cool. And you have that same kind of knowledge. So we have this problem right here that we're basically going to kind of replicate a little of what he did, but we're not going to have to go out and measure things and have someone walk between the cities and figure out the distance. We'll cheat and use some prepared math for us. So Seattle and San Francisco, they're in the same longitude line. So that means they're basically lined up. It's not like different parts of the Earth. They're in a straight line beneath each other, 680 miles apart. So at noon on a summer day, an upright meter stick, 1 meter tall, in Seattle, cast a shadow. Here it is, 2 degrees. Right, not to scale. This is, this is a lot more than 2 degrees. If that was 1 meter, not to scale. On the same day, at the same time, an upright meter stick in San Francisco would have an angle of 7.83 degrees. So we're supposed to use this information to calculate the circumference of the Earth. Wow, we can do that. Right? Some old Greek mathematician dude from 2,200 years ago can do it. You and I can do this. All right, so notice the shadow is different directions. So straight up and down would be somewhere in between them, right? Somewhere in between them. So we got to kind of add both those together because the shadows aren't the same direction. The sun's not the same way. So combined, we're looking at a 9.83 degree difference. That's the difference, right? And so how many pieces of a circle is that? How many times would that go into 360 degrees? Well, let's see. We have another wonderful tool that they didn't have back in ancient Greek. Was this wonderful calculator right here, and we will use it to see how many times 9.83 will go into 360, and it turns out it's 36.62258393, and that's rounded there. That many times. All right, that many times you can make it, that many pieces of a circle. So these cities are 680 miles apart. So if that 680 would be multiplied 36.62225, that would complete the circle. And that would tell us how large the Earth is. So let's do that. Let's multiply 680 miles to the fraction of a circle that we had and see how big the Earth is. 24,903. He calculated 25. We're both less than 100 miles apart. Pretty good. I think we're more accurate because it was below 25. So we're a lot closer, but our measurement of the distance in miles, 680 miles, would be a lot more precise, I would imagine, and we was able to choose these. So 24,903 miles around the Earth. Cool stuff. Same tools as the old Greek guy from 2,200 years ago. But that's what I'm trying to get you to see, guys, that you have so much capability now. You have so many tools in your mouth bag. You just got to put a little logical thinking into it, and you can solve a lot of problems. You can solve a lot of problems in the everyday world around you. And that's one of the things he was doing. He was looking at the world, and he's like, now I wonder, I believe it's round, it's circular. They saw when the Earth passed between the moon and the sun that there was a round shadow on the moon. So they knew a couple thousand years ago, really, that the Earth had to be round. Just not everyone believed it for a long time. But you can solve problems like that. And I think if you really put your mind to it, you might surprise yourself and find some pretty cool ways to come up with the right answer. And if you're not sure, I don't know how I got that, but this is the answer. And it works because you're trying to do something and you try to calculate all that, and it just all falls into place because that math sense that you're building, the ability to figure out the right answer, the right way to do things, even if you don't know the exact equation or exact necessarily the mathematical way that should be done, you might be able to find another way and surprise yourself. So whatever you do, enjoy it. Challenge yourself. Do a little something. All right, this will wrap up this week. Next week we'll have another lesson on Monday, and then Wednesday we'll just kind of do something fun, easy lesson to wrap up the year with before we get to the finals days, the finals week, which won't have actual exams. I have something else fun for you to do. Be watching for that info. I hope it's already to you. I don't know when they're going to send it out, but anyway, do work you can be proud of. We'll see you next time.